Alright, so welcome back to particle physics and the standard model. This is lecture 21. And last time we started getting a glimpse of the cosmological constant problem, right. So what did we do? We constructed the Hamiltonian, for which we first had to solve the Klein-Gordon equation for a spin 0 quantum field, and the solution was in terms of plane waves, where we wrote the plane waves with positive and negative energy solutions in terms of a couple of operators that we called A and B, correct. And the energy of course is given by k square plus m square under a square root. And once we had this mode expansion, we were now able to construct the Hamiltonian using the Lagrangian in the usual way, correct, by using conjugate momenta and so on. And in that process we ended up, after having used commutation relations involving these operators A and A dagger, which we saw were in exact analogy with ladder operators in regular quantum mechanics, correct. So there is an omega here, correct, when we talk about harmonic oscillator. So I am setting h bar equal to 1 here. So in exact analogy with that we had this, we made use of the commutation relations and ended up with a Hamiltonian such that you had a term that you expect with an A dagger A, again just like in harmonic oscillator, but then you have this extra term. This is the signature of quantum field theory as opposed to quantum mechanics. We already had a bare term that we had written down when we documented the Lagrangian. In addition to that, I get an E naught term which we interpret as the 0 point energy, correct. The 0 point energy density multiplied by the volume of the space in which you are working on, right. Okay. And we said that the 0 point energy, you cannot do a mode expansion all the way to infinity, you cannot put infinite momentum into a single point in space. So you cannot, you have to put in a cutoff at some high energy which we called an ultraviolet cutoff, and we ended up with the energy density from the 0 point energy to be this expression, right. It has the correct dimensions because it has 4 powers of the energy cutoff, correct. And then we took this cutoff to be the Planck mass. Why? Because beyond the Planck mass we really do not know whether quantum field theory will work or not. That is when you will have to start describing gravity using quantum mechanics, and we have problems about doing that with quantum field theory, right. So we use that as the cutoff, and we can end up with a value for the 0 point energy, okay, good. Now let us compute what that value is, and something surprising will turn up at this point, alright. So let me write that thing again. Epsilon naught is lambda to the 4th over 16 pi squared, where lambda is around 10 power 19 GeV. Good. So what is this? This is just 10 power 76 GeV to the 4th, right, in the numerator. 16 pi square I can just take as 100 for this calculation, okay. We are just trying to get an order of magnitude estimate, right. And so just like that I am getting a 0 point energy, in fact a 0 point energy density of 10 power 74 GeV to the 4th. Let us convert this to some sensible units that we can intuitively understand, alright. The units I want to go to are GeV per centimeter cubed, that is something that we could begin to understand, okay. So I am going to write down the conversion factors but I highly encourage you to derive these yourself. Okay, so now you already know how to do this using Heisenberg's uncertainty principle, etc., etc. We have, by setting h bar equal to 1 and c equal to 1, you can get all these conversion factors. Okay, every unit that we know of you can always write in terms of GeV and inverse of GeV and so on. All right, but now I am just going to write this down. I know for a fact that a GeV is 5 times 10 power 13 inverse centimeter. Okay, so that means what? I want in terms of inverse centimeter cubed, right? So I can pull out a GeV cubed, that will give me around 10 power 41 inverse centimeter cubed, right? Okay. In fact, to make this even better, let us see this in terms of grams per centimeter cube, okay, not GeV, grams per centimeter cube, because we are much used to grams per centimeter cube, right, in day to day experience. So let me give you one more conversion then. I know that a GeV is about 10 power minus 24 grams. Okay, how do I know that? Because I know what Avogadro number is, right, that is 6 times 10 power 23, roughly 10 power 24, and if I have an Avogadro number of protons, what is that? That is exactly what a gram is, because a proton is roughly a GeV, right. So I just use that fact, and when I put this together, what do I get? I get epsilon 0 is 10 power 91 grams per centimeter cubed. Okay. Now think about that number for a second. Okay, isn't it a tremendously huge number, right? 10 power 91 grams of energy, it is not some mass, right, it is 10 power 91 grams of mass energy that you have per centimeter cubed. This is what is predicted from just having written down a simple spin 0 quantum field theory involving the Klein-Gordon equation, writing down the Hamiltonian. These Hamiltonians are not some abstract things, right. You ultimately ended up with a literal energy density here, which you are multiplying with the volume where in whatever system that you are thinking of, right. In this case, the system is what? The entire universe, correct. You can take any sub volume of the universe. This is where this is what the Hamiltonian is going to be, as long as there is a scalar field, correct. And we do know there are scalar fields. The pion is a scalar field, right. The Higgs boson is a scalar field, etc., etc. So it is not some esoteric theory that we are thinking about. Even for realistic theories, you end up with, just like that, from the 0 point energy, you end up with this much energy density. Okay. To give you some numbers, this corresponds to having enough energy in a zeptometer cubed. What is that? That is basically 10 power minus 63 meter cubed, minus 10 power minus 21 whole cubed. Okay, enough energy in a volume of space that is so tiny to basically unbind what? The entire Milky Way. Tremendous amounts of energy, correct. The binding energy of the Milky Way is, you can go calculate this, right. So whatever it is a 10 power 50 something joules. You have enough energy within just a zeptometer cubed to unbind the entire Milky Way. Okay, obviously that is not what we see here, right. Just because we have quantum field theories to describe the world does not mean the Milky Way has been ripped apart, but we have measured this energy. Okay. So let me tell you what the measurement is, let me tell you what that number is, and then let me give you the physical meaning of this number. All right. um, the measurement, the measured value turns out to be MeV to the fourth, where m is milli, okay, and in our units it is just 10 power minus 31 grams per centimeter cubed. This makes more sense to us intuitively, right. This is such a small energy density that it makes sense, that because we never hear of this in real life, in ordinary life, right, that there is some energy out there coming from quantum field theory, the 0 point energy of quantum field theory, right. So, what does this correspond to? This is the energy, the caloric content rather, in a sugar cube, okay, in a volume of a kilometer cubed. The caloric content of sugar, a sugar cube in a kilometer cube basically, right, and that is a very, very tiny amount of energy density, correct. That is exactly the reason why we do not really hear of this outside of the context of particle physics and cosmology, okay. Okay. So, what do I mean by all this? How did people measure this 0 point energy, right? So, now think about what this energy density means, okay. This is not a function of space time coordinates, correct. This is a uniform energy density all over the volume of space where we think quantum field theory applies, right, and obviously it is homogeneous, but it is also obviously isotropic, correct, it does not pick any direction, none of that we have put in here, correct, and this energy is just there, you just created this energy with this Hamiltonian with the quantum fields, it is just there, it is a 0 point energy you cannot get rid of from Heisenberg's uncertainty, right. So, what would happen if you filled a region of space, right, with uniform energy density like this? What should happen? You expect that space, that patch of space to expand, agreed? Do you remember this from GR? That is what I have done now is exactly describe the FRW metric, right. Remember the FRW metric? You had this, right, you had dx squared plus dy squared plus dz squared, correct. There is probably a square here, I am not sure, but nevertheless this tells you that you are in isotropic and homogeneous space, right. So, when you put this energy density in space, you are making that part of space expand, right, or if that energy density is negative, obviously you are making that part of space contract, right. There is either some stretching or shrinking going on here, right. Now, that is the reason why I began by saying if you put in this much energy into space, you will immediately rip out everything, okay. I mean, if you put this much energy even into a zeptometer cube, you are going to rip out the entire Milky Way because the space is going to expand like crazy and completely unbind it. But even otherwise, if you put in this much energy all over space, the entire okay, so if you put this much negative energy, the entire space would be crunched down to basically a Planck length, okay. So, the Planck mass corresponds to a length scale, right. So, everything, all of space will be crunched down to this very, very, very tiny volume corresponding to the Planck length, much smaller. This is the smallest scale, smallest length scale you can think of. Okay, and if that energy is positive, then space will expand away so fast that you won't see anything beyond a Planck length. So the horizon length will become the Planck length. Okay. Either way, the universe will be a very tiny space, tiny place, and we wouldn't have ended up with such a big universe. The reason the universe is so big is because the 0 point energy, which I can also now call the vacuum energy. Agreed? Vacuum meaning minimum, right? The minimum of all the field configurations that I am thinking of. So because it is so small, we can see a very large universe. Alright. Now, what is this energy also called? In both popular science and also in technical cosmology? This is exactly what people call dark energy. Okay. So remember, there is dark matter, dark energy, regular matter and radiation. These are the different components of energy that form the energy budget of the universe, right. So as far as particle physicists are concerned, the content of dark energy is not so much a mystery. Okay, we know where the dark energy comes from, because to us the dark energy is the same as the vacuum energy, in turn the 0 point energy, okay, and sometimes we also use the word cosmological constant. You must have heard this word before, right? In the context of GR. This is a word introduced by Albert Einstein, right? That in his equations he could not help writing down a constant that satisfied all the symmetries in the problem. So it was compulsory for him to write it down, correct? And that is what we have also done here. Now we have done it from the point of view of field theory, he did it from the point of view of GR, and these two have a very important relationship that we will see soon. Okay? So as far as particle physicists are concerned, the content is not such a mystery, alright, the content of dark energy. What is a mystery is the fact that we naively, using UV cutoffs, we naively expect a value like this, but then we get a value that is, how many orders of magnitude is this? This is 122 orders of magnitude smaller, correct? 91 plus 31. Correct? That really is the mystery actually, not really the content. Why is there so little dark energy? Why is there, although dark energy seems to dominate the energy budget, it makes up 70% of the energy of the universe, it is still too small, too small, okay. So that really is the mystery. There is another way to see this mystery, which is, see, there are two terms here, right. I just calculated the E naught term from the as a 0 point energy, right, but there is also the omega naught term, correct. I did not say anything about the omega naught term. Why? If you recall, that omega naught we wrote down at the point of writing down the Lagrangian itself, agreed. So where is that? Here, there you go. When I wrote down the Lagrangian, I already wrote down the omega naught term, because just like Einstein was forced to write his constant term, we were also forced to write this constant term in the Lagrangian, because it satisfied all the symmetries that we wanted, correct, Lorentz invariance and so on, right. So what about that omega naught term? There is nothing really you can say about the omega naught term, because it is a free parameter of the theory, okay. And That is the term we call a bare term because it's a free parameter that you just had to write down in the Lagrangian and you don't have any control over it. Okay. Now seen in that light, right, let me write down, let me highlight just those two terms. I had an epsilon naught or an E naught minus omega naught. Of course, there's a volume here taken to be the volume of space, right? This was my Hamiltonian. So now seen in this light, you could say that sure, what if my epsilon naught, what if my E naught turns out to be such a large number? I don't care. I always have the omega naught. I have freedom with the omega naught because it's a bare parameter. It's a free parameter. So I can just make them cancel with each other and get whatever number I want. Correct? In this case 10 power minus 31 grams per centimeter cubed and everything is fine. There is no more problems with this. Right? Okay. One could say that, right, there is actually physically absolutely nothing wrong with that argument, okay, but it just makes the whole thing a very, very, very strange affair. Why? Because that means you are asking me to cancel 122 digits, 122 decimal places, correct? This is not just exactly 10 power 91 grams per centimeter cubed, right? It actually has 91 decimal places, right? And then you are asking that to up to 122 decimal places, you want the E naught and the omega naught to cancel each other off, so that I end up with a number that's so tiny that people once used to think it was 0 actually. Agreed? In other words, you are asking that we fine tune, it's a technical term these days, we fine tune the bare omega naught to get the measured value of the dark energy. Let me just call it the cosmological constant. Okay. So these are all interchangeable terms. Dark energy, vacuum energy, 0 point energy, cosmological constant, they are all interchangeable as far as our course is concerned. Okay. So let me just for completeness write, we are asking that this be fine tuned at the level of 10 power minus 122. It just means you want a fine tuning, you want a cancellation of 122 decimal places. Okay. Now that looks very, very, very unlikely, right? And you agree if you buy something, okay, let's not go into the analogy, but it's just a very strange thing that you have to cancel so many decimal places. So this fine tuning is what is known as the cosmological constant problem. And many people consider this the biggest problem in physics, in theoretical physics, and people also call this the worst prediction in theoretical physics. Why? You started with simple principles and then as an immediate consequence you got a number out which turned out to be 122 orders of magnitude off, correct? Now there's a few things, there's a few comments here why this is really a problem, why this problem itself is robust. Okay, you might say, all right, we are talking about one single field here, maybe this is the Higgs field or whatever, but I have other fields also in the problem, right? I have electrons and the W boson, Z boson, photon, etc., etc., etc. What about all of them? They all have a Hamiltonian. They also have a 0 point energy. You cannot escape that due to Heisenberg's uncertainty. What about the contributions of those? I didn't account for those, right? And the answer is those things only make it worse, not better, right? Because all those fields now have a 0 point energy. Whatever they may be, they would all get to an order of magnitude that's around 10 power 91 grams per centimeter cube. That's the contribution from all of them. And then I have to now fine tune the contributions of all these other fields as well in order to get a very small number, right? So let me just write it down. So multiple fields makes things worse. Okay. Another thing you might object to is that I took the cutoff to be the Planck scale, correct? Now we've only measured we've only measured fundamental parameters up to the Fermi scale around 100 GeV, right? So you might ask, maybe in the future somebody might build a very big collider, a planet size collider if you want, and then find that even at 1000 TeV or even at 10 power 4 GeV, the quantum field theory breaks down. So maybe I should not use the Planck mass as the ultraviolet cutoff, I should do something much smaller, okay? But the thing is, even if you use just the Z mass around 100 GeV or the weak scale, right? Even if you were to use the weak scale as your cutoff, what happens? Instead of 10 power, so here I have it, instead of 10 power 76 GeV, let me write down here, if I use lambda as just 100 GeV, the weak scale, then I end up with what? What is lambda to the fourth now? It is 10 power 8 divided by 100. 16 pi square is 100, right? And that is what? 10 power 6 GeV to the fourth, correct? Now notice that even this is still much larger than this. It's now larger than by about 56 orders of magnitude, I think, if I am doing this correctly, right? Nevertheless, all you've done is bring the problem down from 122 orders of magnitude down to 56 orders of magnitude. So that still doesn't solve the problem. That still makes it the largest problem, largest discrepancy in physics. There are many other discrepancies between calculation and observation, but even in this case, you still have a tremendous gulf between prediction and observation, right? So I'll write that also down. Weak scale UV cutoff, problem still persists qualitatively. Well, it's not qualitative really, you can quantify it, of course, so I'll just leave it there, okay? You just made the discrepancy smaller, but the problem as such still persists, okay? There's one more thing here. I told you that these two, right, these two terms seem to be two different contributions to the total dark energy density, right? The bare term, sometimes people call this the bare cosmological constant, okay? So I'll just write that. So this term, which also appears in GR, you can call this the bare cosmological constant, and then once you add up with the other contributions, you get the actual cosmological, effective cosmological constant, okay? There is yet another contribution actually. We will come back to this when we talk about symmetry breaking and so on. So that there's a third contribution coming from the potentials of scalar fields. Okay, what do I mean by this? We are already working with a scalar field, right? But we didn't introduce any interactions at all with of the field with other particles or even with itself. There are not even self interactions, right? But in general, you will agree that in the Lagrangian, not only do I have a kinetic term, right, and not only do I have a mass term like this, I could actually also have introduced terms like these, correct? Lambda 1 if I want to call it, lambda 2, 5 to the 4th and so on. These are all Lorentz invariant, right? I am constructing them using explicitly Lorentz invariant scalars, right? So, all these terms together would now form a potential which contribute to the energy density of the universe. Agreed? This is the kinetic term, so the rest has to be a potential term just involving the scalars, right? In that case, I can have potentials of, I can draw V of phi versus phi like this. I can have potentials of many forms at this point, right? And these potentials actually, what do? They literally deposit or dump energy in space, right? This is exactly, when we say the field fills space and all that, it comes with the fact that using in the potentials of these fields, the field configurations basically literally dump energy density at all points in space uniformly, right? Just like the cosmological constant, it's constant because it's uniform all across space and time. Similarly, these potentials would dump energy uniformly at all points in space. So, in other words, that's another masquerader of dark energy, right? It's another contributor to dark energy. So, that's what it is. Then you might ask, what about this contribution? What does this do? Again, it's like this. Once again, this only makes the problem worse. Why? Because now you have to fine tune 3 different kinds of contributions, right? 3 classes of contributions, one from the 0 point energy, another from the potentials, and the third one from the bare cosmological constant term. So, there is no way to escape from this problem, okay? The problem is there actually. It depends on your taste. If you can live with such fine tuning, such very improbable looking fine tuning, then well and good. A lot of people do live with it. But nevertheless, the fine tuning is there, and if you think you want to explain this coincidence with some physical mechanism, then it's a very interesting problem, okay? And there are many interesting solutions that have been put forth. So, okay, so I'll end the lecture here. So that wraps up our discussion of the cosmological constant problem, where you see that even these cosmological stuff are all interconnected with particle physics, right? There is no escaping from all these. But in the next lecture, we will take up complex scalar fields and introduce the concepts of antiparticles and so on, and from there we will move on to other spins, spin 1, spin half and so on, okay? Alright, thank you. See you in the next lecture.